Hello everyone, welcome to the course of ultrasonic testing technology. The main content of this course is the scanning speed and its adjustment method in ultrasonic testing. Through the study of this lesson, I hope to achieve the following teaching objectives. Master the definition of scanning speed in ultrasonic testing. Master the adjustment method of longitudinal wave scanning speed. Master the adjustment method of shear wave scanning speed. First, what is the scanning speed? Horizontal scale value of the echo on the oscillograph screen of the instrument ratio with the corresponding actual sound path in the workpiece is called the scanning speed, also called the baseline scanning ratio. It is similar to the scale on the map. For example, the scanning speed is 1 to 10, and the horizontal scale on the oscillograph screen of the instrument represents the actual sound path of 10 mm. The significance of adjusting the scanning speed is to locate the position of defects in the workpiece. What are the differences in the adjustment of the scanning speed of ultrasonic testing under different waveforms? Next, we will first learn the adjustment method of longitudinal wave scanning speed. Longitudinal wave flow detection generally adjusts the scanning speed according to the longitudinal wave sound path. The specific method is to align the longitudinal wave probe with the flat bottom of curved bottom with appropriate thickness, so that the two different bottom waves are aligned with the corresponding horizontal scale values. For example, to detect a workpiece with a thickness of 100 mm, if the scanning speed is 1 to 2, is adjusted. The equipment model is CTS-22A, and the CSKIA test block is used to adjust it. As shown in the figure, align the probe with the bottom of the surface of the test block with a thickness of 100 mm. Adjust the depth, fine adjustment, and pulse shift knobs on the instrument, so that the bottom echoes B1 and B2 are aligned with the horizontal scales 50 and 100 on the oscilloscope screen, respectively. At this time, the ratio between the horizontal scale on the time-based scanning line and the actual sound path is exactly 50 to 100 or 100 to 200. That is, the scanning speed of 1 to 2 is adjusted. Compared with the adjustment of P-wave scanning speed, the adjustment method of S-wave scanning speed is relatively complex. There are four important parameters in ultrasonic transverse wave of flow detection: horizontal distance L, reflector depth H, ultrasonic sound path S, ultrasonic refraction angle beta. Horizontal distance refers to the distance from the incident point of the probe to the projection point of the reflector on the workpiece detect surface. Depth H refers to the depth of the reflector from the workpiece detection surface. Sound path S refers to the straight line distance between the incident point of the probe and the reflector. That is, distance that the ultrasonic wave reaches the reflector. Refraction angle beta. It is a parameter describing the inclination of the ultrasonic beam emitted by the probe. It can be seen from the triangle relationship in the figure that if any two of the above four parameters are determined, the other parameters will also be determined. Therefore, it can also be said that the defect position in the workpiece can be determined by any two of the four parameters. Therefore, there are three methods to adjust the S-wave scanning speed: sound path adjustment method, horizontal distance adjustment method, depth adjustment method. Sound path adjustment method. It refers to the horizontal scale value on the oscillograph screen with the echo of the reflector method of representing the scanning speed by the ratio of a transverse wave path corresponding to the reflector. horizontal distance adjustment method. It refers to the horizontal scale value on the oscillograph screen with the echo of the reflector. The scanning speed is represented by the ratio of the horizontal distance corresponding to the reflector. Depth adjustment method. It refers to the horizontal scale value on the oscillograph screen with the echo of the reflector, and the scanning speed is expressed by the ratio of the depth value of the reflector. Among the above three methods, the depth adjustment method and the horizontal adjustment method are more commonly used. The depth adjustment method is mostly used for S-wave floor dictation of thicker workpieces, while the horizontal adjustment method is mostly used for S-wave floor dictation of thinner workpieces. Next, the specific use methods of the depth adjustment method and the level adjustment method are illustrated as you can see here. Example 1. The method of adjusting the scanning speed of 1 to 1 by using CSKIA test block according to the depth adjustment method. As we can see shown in the figure, this is an example, and we can learn from the trilateral relationship with the right triangle. As we can see from these formulas, we can see and get the result. Next, we will first calculate the horizontal distance h1 and h2 corresponding to the two circular arc surfaces of R 50 mm and R 100 mm detected by the angle probe. Then place the angle probe at the center mark position of the two concentric arcs on the test block. Align the probe with the two arcs to emit ultrasonic waves and translate the probe in the horizontal directions to maximize the reflected echo of the arcs. Then we adjust to the depth, fine adjustment, and the pulse shift on the instrument to align the R50 regular arc echo B1 and R100 circular or echo B2 with the horizontal scales of H1 and H2 on the oscillograph screen so that the scanning speed can be adjusted according to the depth of 1 to 1. Example 2. Method of adjusting the scanning speed of 1.1 according to the horizontal adjustment method. As we can see in these formulas, the scanning speed of 1.1 was adjusted horizontally by the CSKIA similar to example 1. As we can see, then calculate L1 and L2 respectively by using the derived formula. Place the angle probe at the center mark position of the two concentric arcs on the test block. Align the probe with the two arcs to emit ultrasonic waves and translate the probe into the horizontal direction to maximize the reflected echo of the arcs. Then, we adjust the depth, fine adjustment, and the pulse shift on the instrument to align the R50 circular arc surface reflected wave B1 and R100 circular arc surface reflected wave B2 with the horizontal scales of H1 and H2 on the oscillograph screen so that the scanning speed can be adjusted according to the horizontal distance of 1 to 1. Example 3. Use CSKIA test block to adjust 1-to-1 scanning speed according to horizontal distance. As we can see, we have learned the specifications of CSKIA test block and its internal setting short transverse hole reflector. Now select two short transverse holes and with depths of H1 and H2 respectively, and calculate the horizontal distances L1, as you can see here, corresponding to the transverse holes and A and B detected by the angle probe. Then use the angle probe to detect the short transverse hole and translate the probe to reach the highest reflection position. Adjust the instrument to align the initial wave T and the echo A of the short transverse hole on the oscillograph screen with the scales 0 and x1 respectively. Then detect another short transverse hole B and translate the probe to reach the highest reflection position. Set the reading of the echo B of the short transverse hole as x2. In order to make the horizontal scale value on the oscillograph screen directly reflect the time or distance ultrasonic propagation in the workpiece. Then, return wave on the oscillograph screen needs to be moved to the left. As you can see here, this operation is called zero position correction on the angle probe. Now, as the formula shows that the principle used in this formula is that the ratio is horizontal distance in the workpiece when the ultrasonic wave propagates to the short transverse holes, and B is equal to the ratio of horizontal scale of the instrument. Then, as we can see here, the formula. Next, use the pulse shift knob of the instrument to move echo B leftward. By the functioning of the pulse shift knob is to translate all echoes on the instrument screen as a whole. So, echo A also move left forward, and then use the depth fine adjustment knob to rotate the counterclockwise to stretch the echo spacing on the screen as a whole. And finally, stretch echo B to the alignment scale L2. Since the function of the depth fine adjustment knob is to compress the echo spacing on the screen as a whole, without changing the echo scale proportion formed before stretching or compressing the wave distance, echo A also returns to L1 in this process. So far, this scanning speed is adjusted, and according to the horizontal distance 1 to 1. Okay, that's all for this class. See you next time.